Hello, welcome to our first EE2114 Circuits 2 online lecture for spring semester 2020. I hope all of you are hanging in there and doing okay because we certainly have it's certainly an interesting set of circumstances, really uncharted territory that we're in. But I think we can work together to get through this. Um, Along the way here, obviously, if you have questions about the technical information in the course, please don't hesitate to let me know, but also don't be afraid to get in touch with me if you have questions about the logistics of the class or administrative issues or anything like that. Um, there are probably going to be some things come up that none of us have thought of yet, so we'll work our way through it. But communication is key, so please keep in touch and get in touch with me as quickly as you can about things, and we will find a good way to move forward. So our first session here is just to essentially remind us of where we're headed right now in the class. Our last discussions had to do with voltage gain calculations, predominantly for operational amplifier circuits, but essentially we're talking about input-output relationships for any linear circuit. In our case, linear circuits are predominantly going to be circuits with ideal components in them that consist of resistors, inductors, capacitors, and operational amplifiers. Um, when we studied steady state circuit analysis, what was going on there was we basically looked at a way to represent um, sinusoidal signals using phasors, and that was essentially a way to characterize two of the three uh, parameters needed to describe a cosine wave. If you recall, we need to have the amplitude, frequency, and phase. And a phasor is a particular notation that uses complex numbers to represent something that is related to the amplitude, and we call it the magnitude. And in our case, the magnitude of our phasors is the RMS value of the waveform. And then we also represent the phase of the waveform. The frequency information is essentially understood in the background. You don't have to have the frequency information to represent the phasor. Now, why does it work this way? Well, if you recall, the impedance of our passive components. For a resistor, it is just the resistance, but the impedance for inductors and capacitors is frequency dependent. But once you've established the frequency, you can actually write the impedance as a complex number. For an inductor, it's going to be J times something, J omega L. And for a capacitor, it's going to be 1 over J omega C. So those two values, which by the way, you can represent the capacitance, the impedance of the capacitance as negative J over omega C. So once you have things written that way, you can then do circuit analysis using techniques that are essentially the same as you've used for DC, except now we're using complex arithmetic to arrive at representations of currents and voltages. So let's first look at, if you recall, the phasor for, we'll call it our input voltage, because we're going to talk about our circuit network here in a moment. So we would write the phasor as something we're going to say VI. That's our input phasor. Okay, so V sub I, and that's going to be equal to something that looks like the magnitude of VI, and that's going to be at an angle theta I. Okay, no real surprise there. And we know that that relates to a time domain representation that would be VI of t, which equals the magnitude again of the phasor times the square root of 2, right? The magnitude of the phasor is the RMS value. We have to multiply the RMS value by the square root of 2 to get the amplitude of the cosine. And then we have the cosine omega t plus, and then there's an angle associated with the input voltage, theta I. All right, so no surprise there. We have the amplitude, we have the frequency, and we have the phase. Now, again, the phasor, as I've already discussed, doesn't need to have the frequency information in it because that is already understood. You do have to know it, however, if you want to do a conversion from inductance or capacitance to impedance. So keep that in mind. Now, what's going to happen is we're going to have this input voltage. It's going to be the input to something that right now we're just going to refer to it as a general, what we'll say is a two-port network. So we have our input and we have our output. And so we would say VI of t is here, and V out of t is over here, and this is our circuit. We'll just label it with a C. So that circuit, it could be a complicated network. It could be something fairly simple as a simple RC filter. So no surprises there either. But we have to be able to do the analysis. We would convert the input voltage to its phasor. We would convert all the uh, component values in the circuit to their particular impedances, and then we would use circuit analysis techniques to come out with the phasor representation of the output voltage. And then we could take that phasor representation and reduce it back to the time domain, because a lot of times what we're interested in, no pun intended, is the time domain representation of a waveform and how it relates to some other system or process or something like that that we're dealing with. So how do we come up with that? Well, we do the circuit analysis. We arrive at something that we'll call VO, the phasor for the output voltage. And that we can say, and these are all generic representations, obviously, but our V out would be our magnitude of VO, which is going to be the RMS value, and it's going to have some angle theta O. Okay, and that's going to correspond to a time domain waveform. Now, there's a little bit more to this calculation, obviously, if we want to find that out, and that's where this voltage gain expression comes into play. So we are going to say that this circuit, represented by our circuit here, C, that it's going to have a voltage gain, and we're going to, again, write this in the frequency domain because we're dealing with phasors that have to do with a particular frequency, but we say A sub V is going to equal the ratio of the phasor V out divided by the phasor V in. Okay, so again, that's no surprise. We've done this many times now. Okay, so it should be something that you're starting to get used to. Now, again, the complex arithmetic can be a little bit hairy. Sometimes it can be frustrating. Solving the circuits can be hairy and frustrating, especially if you have to solve more than just a couple of equations and unknowns. So again, those are things that you just got to kind of practice and get used to. But there's, essentially nothing new there that's beyond what you've done in DC analysis. But this concept of this voltage gain, now we want to take this a little bit further and get to this concept of the transfer function. Okay, so but there's a few other things we want to talk about along the way. Okay, so this voltage gain, we can write it out. Since it's a phasor, again, we can write A sub V equals V out phasor divided by V in phasor. And we can basically write that as something that looks like MA at an angle theta A. So there is our voltage gain represented as a complex number. And obviously we know that we can cast V out, the phasor, as AV times VI. Both of those are phasors. So let's decompose that a little bit. So we can write V out, the phasor, which is equal to something that looks like MA at an angle theta A times the magnitude of VI phasor at an angle theta I. Okay, again, no real surprise there, which we can rearrange and write it as MA times the magnitude of VI times the angle, which is the sum theta A plus theta I. Again, no surprise. Now we can take the phasor for V out and convert it back to the time domain, which would give us the expression. Remember, what do we need to represent the signal in the time domain? Well, we need to know the magnitude or the amplitude of the signal. Well, here is the magnitude, the RMS value, right? And then we also have the phase here. And the frequency, again, as I've talked about, is understood. We know what the frequency is because we've worked the problem with a particular frequency on the input side. So we're going to be able to write V out. We have to find the amplitude, which is the RMS magnitude times the square root of 2. Okay, so we're going to be able to write V out of t equals the quantity MA times the magnitude of the input phasor times the square root of 2 times the cosine of omega t plus, now we have to have both angles in here, theta A plus theta I. Again, so this should be no surprise. This is nothing new. We've talked about this probably more times actually than we need to, but I do want to make sure that everybody understands what's going on here because obviously we're going to take this a little bit further and to get to our transfer function representation and our ability to talk about frequency response and Bode plots and things like that, which is topics of chapter 14. So that's where we're going to head with this. Before we move on, I do want to tidy up something. I have referred to AV a number of times as a phasor, and that's technically not the correct way to refer to it. Now, it is a complex number, which was the point that I was trying to make by reinforcing the fact that you understand that it's a complex number. Obviously, it's generated by dividing V out, that phasor, by Vn, which is also a phasor. So it's going to generate something that clearly, if we look at it, it has a magnitude and it has a phase. So it is a complex number. So structurally, it appears as a phasor, but AV does not represent a waveform or a signal. It actually represents the complex gain of the circuit, which we're going to develop a little bit of different nomenclature as we move on. But one other point I also wanted to make, which we've talked about when we were in class, but what does AV actually do to the time domain waveform? So we had this input voltage, which had a magnitude that actually we see that, or the amplitude, which was the magnitude of the VI phasor times the square root of 2. So that was the amplitude of the input signal. And the phase of the input signal is right here, theta I. So both of those appear at least indirectly, in the time domain representation of the output waveform. Now, the difference then is that the amplitude of the output is also multiplied by this magnitude VA, or MA, which is the amplitude or the magnitude of AV. And then we also shift the phase of the output signal with respect to the input by an angle theta A, which is the angle of AV. So AV does clearly represent the magnitude and phase shift of the input as it becomes the output signal. Notice something extremely important. The frequency does not change. So keep that in mind. The frequency remains the same. That is a very important facet of linear systems. So now we got to think about what we would do in the situation where the frequency of the input voltage changes. Doesn't mean that it's changing continuously, but what happens if we have a input voltage signal with some frequency omega 1? Well, we can do what we've already been talking about and compute the gain of that system, that linear network, and we would call that gain A sub V. But to be more clear then, I want to say, well, I really would like to call that gain A sub V of omega 1. So I really want to say this gain is a function of frequency. And let's put our little vector hat on there so that we know that that's actually a complex number. but it's going to be a complex number at that particular frequency. But now if I write it that way, I can evaluate A sub v functionally um, as a function of the frequency parameter omega. So normally we would start out then really by looking at this generically as AV of omega, just generically, where omega is the generic frequency argument to this function. And so that's where we're headed. Now, that notation really isn't something that we use all the time, but it's at least a good place to start because that's how we defined our voltage gain. So we'll talk about it that way. But more commonly, we would write the voltage gain. It would be more or less something that looks like H of omega. Okay, so we would tie those things together. And we really don't put um, the overbar representing it as a vector quantity because now it starts to get a little bit different because now we're really talking, yes, it is a vector quantity, but it's a frequency dependent function. Okay, so but we're going to write that as h of omega, and we're only going to do that for a moment because we're really going to move along and say, actually, I want to write that as h of j omega. Now, the reason for that is because when we look at the impedances of the various components, right, whenever there's an omega, there's a j right next to it, or generally there is. It depends on how you treat it, obviously, right, because as we know, the impedance of a resistor is the resistance, the impedance of the inductor. If we have L, that impedance becomes J omega L. And if we have a capacitor, then the impedance is 1 over J omega C, which equals, here's the only thing we got to worry about is we have negative J over omega C. Now, we might not want to always write it that way. We may want to actually leave it represented this way when we build out the functional expression that determines the voltage gain of the circuit. And the reason for that is to help us manipulate terms and come up with some reasonable representation that's common and standardized across how we represent these linear systems. Okay, so what we're going to have is um, a way to represent the system as something that we introduced right before the break that was called a rational polynomial function, right? So we had um, something that looked like a polynomial divided by another polynomial, and that can seem fairly complicated, but we're going to build up the structural foundation of that in this discussion. So we'll build up that structural foundation using an example that we've looked at a number of times before because it's simple and easy to work with. And so we're going to have our two-port network again be our simple RC filter, right? So we have our resistor and we also have a capacitor. Okay, so the resistance value is R, the capacitance value is C. Okay, so there's no surprise there. We're going to have our input over here, VI of t. Looks like I ran that off the page a little bit. Let me fix that up just a tad. So we're going to have our input here be VI of t, right, from here to here. And our output is going to be taken across the terminals here, VO of t. Okay, so we've worked this circuit many times. We've talked about it strictly in the time domain and differential equations when we've talked about it a bunch of times in the frequency domain. So how is it that we analyze this? Well, first of all, we got to write this circuit in the frequency domain or draw it in the frequency domain. So again, we know the resistance, the impedance there is just R, and the impedance of the capacitor is 1 over j omega c. And so we'll go ahead and just draw that maybe using just boxes here because we really don't care what the particular values are. We just make sure we need to keep track of them, right? So there we have again. Now we're going to talk about our voltages here. Oops, that's not our output. We've got our input voltage and we've got our output voltage, and we've got over here, we've got ZR equals R, and over here, we've got ZC equals 1 over J omega C. Okay, so now this is a simple voltage divider, so we can say, well, V out, the phasor, remember these are phasor quantities now, we're in the frequency domain, we've assumed that we have some frequency omega, and so we're going to say V out, right, is going to be the input voltage, right, times 1 over J omega C, that's the impedance here, divided by the sum, R plus 1 over J omega C. Okay, so it's going to be that expression. And then we can do a little bit of gymnastics with the terms, and we can write that as VI VI times the quantity 1 over J omega RC plus 1. Okay, so if you notice, this thing is what we would call the voltage gain, because we would take both sides, divide by our VI, so we would have V out over Vn is going to be this expression, 1 over the quantity J omega RC plus 1. So given this expression, we could write H of J omega equals 1 over J omega RC plus 1. Okay, and that is something that's an important expression that describes entirely the input-output characteristics of this linear system. It does it in the frequency domain because this expression has to do with frequency. Obviously, we have omega right here. H is going to evaluate to a complex number depending on where you evaluate it in frequency. Obviously, if we evaluate it at the frequency omega equals 0, then we would just get 1 over 1. Well, you'd say, well, that's not a complex number. And I could tell you, well, it's actually the same as the complex number 1 plus J0. So yeah, we can equate it to a complex number. And then as omega gets large, we know that the omega term would dominate in the denominator, and the magnitude of that complex number would dive towards 0 as omega goes toward infinity. Okay, so there also is a phase associated with that complex number. So let's talk a little bit about what that looks like. Okay, so what do we got here? We have our function h of j omega equals 1 over j omega rc plus 1. Okay, so it's a frequency-dependent function that evaluates at any given frequency to a complex number. The magnitude of that complex number is going to be the magnitude of our function h, and so the magnitude is going to be the magnitude of, yes, you guessed it, 1 over j omega rc plus 1, right? And because of the way that the magnitude will work, that's going to be equal to the magnitude, and I'll write 1 more clearly to distinguish it from my little magnitude bars there, and divided by, it's going to be the magnitude of 1 divided by the magnitude of j omega rc plus 1. Okay, well, we know how to deal with that, and so I'm just going to say that's going to be 1 over, and the magnitude of the denominator, well, it's just going to be the quantity omega rc squared plus 1, or 1 squared, right? And then that whole thing square rooted. Okay, so that's no surprise. I could extend the square root over the entire fraction, but I know I don't need to do that. So that's going to be the magnitude of the frequency-dependent gain function. Before we move along, I want to make one comment, or I want to reinforce a comment about the magnitude. Okay, so we're going to talk about our magnitude using the expression we have, right? Our magnitude is the absolute value from a complex variable sense of h of j omega. Okay, no real surprise there. So what does that mean, again, to reinforce? For omega equals 0, so we're operating at dc, then we're going to have that the magnitude, which is our expression right here, right? We can evaluate that, as we said, for omega equals 0. Well, that's really not hard to do. We just have um, the magnitude at omega equals 0 is h, the magnitude of h of j0, which just equals 1 divided by 1, which equals 1. Okay. Now, as we go higher in frequency, we have to use a limit now. So we have the limit as omega goes toward infinity of the magnitude of h of j omega. Well, again, we see that the omega will dominate in the denominator of this expression, cause its expression to become increasingly large. Matter of fact, it's unbounded. So we're going to take 1 divided by an increasingly um, larger number. So in the limit, that's going to go to 0. It's never going to actually get there because we can't get to infinite frequency, but it's going to approach it. The higher the frequency, the smaller the magnitude. Okay, so now we're going to talk about the phase. Again, just to remind us of what this function looks like, again, for this particular simple RC circuit, we have that h of j omega equals 1 divided by j omega RC plus 1. Well, how do we compute, looks like I cut off the edge of my h there, how do we compute the absolute value of this complex number? Well, it turns out that I'm sorry, the phase of this complex number. Well, it turns out we have to look at the numerator and the denominator separately. Okay, so I can write this as this is going to be 1, and I'll write again 1 a little more clearly, at an angle of 0 degrees. Okay, that's pretty obvious. Divided by something that might take up a little bit more room. So I've got the magnitude of the denominator, and that's going to be again, the square root of the quantity omega RC, that quantity squared plus 1. And then the angle, well, I've got to take the arctangent of something. Okay, and we'll extend this out here. This arctangent is going to be of the, right, it's the arctangent of y over x in generic terms. So that's going to be the arctangent of the complex part divided by the real part, which happens to be 1, so it's just the arctangent of omega RC. Okay, so now that's going to be in radians, obviously, in this angle up here. Well, we can write it as degrees or radians. It's 0 in any case. So now what I have to do to write h of j omega, again, we've already done the magnitude calculation, but I'll go ahead and write it in here just to keep this thing as being complete. So h of j omega, right, is going to be 1 over the square root of omega RC squared plus 1. And the angle is going to be the 0 angle, again from up here, minus this angle, right? So it's going to have to be 0 minus the arctangent of omega RC. Okay, so it's just going to be the negative of the arctangent of omega RC. Okay, so that's going to give us the complex form for h of j omega. It's the magnitude here and the phase here. Okay, so now what we want to do is take a look at what actually happens to this phase as we change frequency. So what happens to the phase here as we modify frequency? Well, the first thing is, so the phase We want to talk about the frequency first. The frequency, if omega equals 0, then the phase, and I'll write it here as the angle of h, right? That's going to be, well, if we put in 0 for our frequency, we get the arctangent of 0, which happens to be 0. So then I'll just write it here, our phase equals 0. And then again, now we can't pick, we can pick larger and larger and larger frequencies, but what we're going to find is as omega goes to infinity, then what we're going to see is the limit as omega goes to infinity of negative, don't forget the negative, arctangent of omega RC equals negative 90 degrees. And that probably doesn't come as a surprise because as we get larger and larger in frequency, the frequency response sort of looks more and more like the frequency response looks more and more like something that looks like just 1 over j omega RC. If omega is very large, keep that in mind, then the plus 1 here makes almost no difference. So that plus 1 can almost be ignored, and we just look at something that looks like 1 over j omega RC. Well, that kind of looks like the impedance of a capacitor. And so the capacitor has a phase angle of negative 90 degrees because it essentially looks like something like 1 over j times a number. And so that's really what we have here. So that's another way to think of the response characteristic of this simple low-pass filter. And that probably won't come as a surprise to you. So now where we're headed in our discussion now is to look at what happens, how do we want to represent this voltage gain characteristic. Um, we want to be able to look at it in some compact way as a function of frequency. Well, one is to actually write the function, but that's not always really obvious what the function is going to do, how it's going to behave. So really what we want to do is be able to evaluate h of j omega, evaluate that. We want to evaluate at many frequencies. And plot it. Now, we got to be careful how we plot it, but this plot um, is going to be a plot of the frequency response of the system, right? The circuit has a frequency response. It responds to frequencies in different ways, different frequencies in different ways, because the impedance of the reactive components changes as a function of frequency. So the particular frequency response plot that we want to most commonly deal with is something called a Bode plot. And a Bode plot is a frequency response plot. It plots the frequency response, and in particular, it plots the magnitude versus frequency and the phase versus frequency. And that's going to be the topic of our next lecture. Before we go, I want to wrap back to one thing. I said we were going to develop the structure for our h of j omega, which is going to become our transfer function. We're going to call it h of s. I think we've got enough material in this particular segment, so I'm going to also push that into a later segment. But just to summarize at least for our simple example. So we had, for the simple RC low-pass filter, we had h of j omega is 1 divided by j omega RC plus 1. Now, what we're headed toward for our transfer function representation is actually to do a variable substitution. We're going to say that S equals j omega. Okay, really all it is to simplify some of the notation and the mathematical algebraic operations really we're going to deal with. So what that leads to then, we can rewrite h of j omega as h of s, and that's going to be 1 over SRC plus 1. So again, we talked about this in class before break, but I do want to, again, the purpose of this lecture is to kind of reinforce some of these topics and get us headed back in the direction that we were headed before the break. So if you notice, this really has a structure of a numerator polynomial in S divided by a denominator polynomial in S. So we got two functions of S, a numerator and a denominator. Now the numerator is a boring function. It's a polynomial, but actually all the S terms, all the coefficients for the terms where the powers of S are greater than 0, all those coefficients are 0. So it's a boring one. It's just 1. The denominator is not a whole lot more interesting in this particular case, but it is a first degree polynomial in S, right? So we have the variable S here. This is the coefficient for the term that has S to the first power, and this is the coefficient 1 for the term as a 0. So this really is a rational polynomial function, and we're going to discuss in later lectures why we do it this way and where we're headed. So just wanted to leave you with that. Have a good day. Thanks for listening.